In the last video, we talked about the idea of measures of center as a way to encapsulate the data into one representative number. But the question is that enough? Can we do a little bit better? Can we add an additional number? And let me talk about why it's good to have some additional numbers to give other ideas about data just besides the center of the data. So imagine we have these two data sets, data set 1 and data set 2. So if we use the idea of measures of center to describe this data, what do we get? Pause the video now and have a quick go at working out both the mean and the median for both data sets. Okay, so you should find that the mean for data set 1 and the median for data set 1 is 0. And also the mean for data set 2, maybe I'll put a 1 here because it's the first median. The mean for data set 2 and the median for data set 2 is also 0. But these two data sets aren't particularly the same. So maybe think of a way of describing, just qualitatively, how these data sets differ. How does data set 1 differ from data set 2? Just come up with some sort of description. How would you describe to somebody how these differ? And probably the word I would use, or the phrase I would use, is data set 2 is more spread out than data set 1. So you can see with data set 2, if we were to graph that on a number line, let's just a little sketch here. Here's 0, -5, -10, -15, 5, 10, and 15. So data set 2 would look something like this. Where data set 1 isn't as spread out. It looks more like this. 1, 2, 3, -1, -2, -3. Again, this is only a sketch, obviously. The number line isn't evenly spaced or anything like that, but it gives you an idea of what's going on here. So maybe a good number to include would be some number to describe how spread out the data is, or the variability of the data. And that's what we're going to talk about now. So maybe let's write that down. So data set 2 is more spread out or maybe a better word would be variable than data set 1. So what we're going to come up with on the next slide is a few different measures to quantify the variability of data sets. So one kind of naive measure, kind of the easiest measure to talk about, is something called the range of a data set. And all the ranges, it's the largest value minus the smallest value. So the range for data set 1, well, the largest value is 3, and the smallest value is -3. So the range is, of course, 6. And you can see on a number line, if we were to graph these, 0, 1, 2, 3, -1, -2, -3, that if you were to measure the distance between the largest and the smallest point, it is 6 units in distance. So that's all you're doing when you're talking about the range. And the range of the second data set, same idea, is going to be the largest, 15, minus the smallest, which says our data is spread out over 30 units. So that's great in some sense, but I do want to point out one issue with range. It's not used too often for a good reason. And the reason is, of course, it's very susceptible to extreme data points. So, what I mean is that if you had a data set that looked like this, negative 15, let's in fact put data set 2 again. 0, 5, 10, 15. The range for this one we just worked out was 30. But this data set as well, let me write this one down. It's going to be minus 15, minus 14, minus 13, minus 12, minus 11, minus 10, and then 15. So the range of this data set is also 30. But you can see that these are a lot different. In the second data set here, most values are around minus 12, minus 13, in the range from minus 15 to minus 10. And we just have this kind of outlier data point, this extreme data point, positive 15, that's skewing the range. So that one extreme value can really influence a range. So while this is a nice, quick, and dirty measure to calculate, it's probably not the best one for us. We're going to introduce another one. So I guess we could sum up the problem with the range. It's very susceptible to extreme data points, and maybe we'll call this 1. And the second thing, it's very related, but it only has, or only uses, info about 2 data points. The largest and the smallest. And it says nothing really about the data points in between. So we want to come up with a measure that uses information about all the data points in your data set. That'll be a little better for us. So the measure we're going to come up with is going to be called the mean absolute deviation. And you might see it abbreviated MAD or MAD. Now, it's not the standard one that's used in statistics. That's called the standard deviation. We'll probably talk about that a little more later in the course, but it's relatively the same idea. We want to know the average distance of each point from the mean. So we worked out in the previous slide, or a previous slide, that the mean for this data set, this is data set 2, the mean was 0. So we can work out the average distance by finding all distances of each data point from 0 and then just taking the average of it. So adding them together and dividing by the number of data points. So let's go ahead and do that, and then I'll write down some notation for it. Okay, so we'll start from left to right. Our mean is 0. Maybe I'll put a little blue dot here. That's our mean. Okay, well, the distance from negative 15 to 0, well, that's 15 units. We don't care if it's in the negative or positive direction. We just want a distance. Okay. Then we have from 10 to 0 is, of course, 10. From 5 to 0 is 5. From 0 to 0, that's the next data point, is, of course, well, there's no distance. It's 0. Then we have finally, I shouldn't say finally, but on the other side, from 0 to 5 is 5. From 0 to 10 is 10. And from 0 to 15 is 15. So we worked out all 7 distances from each data point to the mean. So what we're going to do is we're just going to add them all together and divide by 7. We're going to take the average of all distances. So it's going to be 15 plus 10 plus 5 plus 0 plus 5 plus 10 plus 15, and that's all over 7. And if we add those together, we get that's going to be 30, 40, 50, 60 over 7, which is roughly 8.57, rounded to the nearest hundredth. What about the other data set 1? So this is, I should say, this is the mean absolute deviation for data set 2 from the previous side. Data set 1, well, again, let's write down the data set. Maybe we'll just graph it on a little small number line here. So we had 0, 1, 2, 3, -1, -2, -3. And again, we can work out all distances from the mean. We know the mean of this data set is 0. And our distances are, of course, 3, 2, maybe I'll go down here, 1, 0, 1, 2, and 3. So let's work out the average distance. 3 plus 2 plus 1 plus 0 plus 1 plus 2 plus 3 over 7 is 12 over 7. And if you work that out, that ends up being roughly, to 2 decimal places, 1.71. So on average, each point is 8.57 units away from the mean in data set 2. And on average, each data point is 1.71 units away from the mean of 0 in data set 1. So just looking at these, you could say that since this data set has the larger mean absolute deviation, this is a more variable data set. That number here, since it's larger, tells you that the data set is more variable. It's more spread out. And that's a nice use for mean absolute deviation. Okay, so in general, we can calculate the mean absolute deviation by finding the distance between each point and the mean. So we take the data value for each point and we subtract the mean from it. And if it's negative, we don't care. And that's why we have these absolute value signs here. So these there, of course, are your absolute value. And as a reminder, absolute value signs just mean whatever's inside of them. If it's negative, make it positive. That's all that the absolute value signs mean. So we don't want negative distances. We just want the unsigned distance. Okay. So for each point, if we have n data points, I just call them x1, x2, all the way to xn. I put some dots here just because I can't write out all of them. So if we had n of them, then we calculate the mean, and for each data point, we find the difference between the mean and that data point, take the absolute value because we don't care if it's positive or negative, and then take the average of all of those distances from the mean. So that's the idea. So let's do this example down here. We have 10 data points. Maybe it's a good exercise for you guys to pause the video and see if you can work out the mean absolute deviation of this data set. Okay, so the first thing we need to do to calculate the mean absolute deviation, well, we need to calculate the mean because we're interested in the differences between each point and the mean. So let's calculate the mean. We'll add together all entries. Maybe I'll put brackets around the -2 here. Plus 7, plus 3, plus 9, plus -3. And how many data points is that? That is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what does our numerator end up being? Well, if we add this together, -2 plus 4 is 2, plus 6 is 8, plus 11 is 19, plus -5 is 14, plus 7 is 21, plus 3 is 24, plus 9 is 33, minus 3 is 30. So our numerator is 30, and our denominator is 10. So we're lucky in this case. We get a mean that is a nice integer, which makes our life a little bit easier in terms of computation. But a lot of times, your means won't be integers. They'll be some rational number, some decimal. So that's okay. It just makes the computation a little harder, but the ideas stay the same. So the first thing we did was we calculated our mean. That's great because we were interested in the distance of each point from the mean. So now, let's find the distance of each point from the mean, add them all together, and divide by 10. So now our MAD is going to be, well, it's going to be the absolute value of the difference between each point and the mean. So -2, subtract 3, that's 5. And we're going to keep doing this for each point. 4 minus 3, 0 minus 3. There are absolute value signs. So are these. I'll make the absolute value signs a little bit darker, so you're not getting them confused with ones or something like that. 6 minus 3 plus 11 minus 3 plus -5 minus 3 plus 7 minus 3. And I'll kind of go down to the next line here just because I'm running out of space. Plus 3 minus 3 plus 9 minus 3. And finally plus -3 minus 3. And we're going to, of course, divide all that by 10. Let me make a little more room. There we go. So let's figure out all of these. And remember, if we calculate something and it's negative, then we're going to make it positive. That's what the absolute value means. So -2 minus 3 is -5, but we want the absolute value of -5, so that's going to be 5. And maybe I'll just explain again really quickly. I'll do a kind of up at the top here. If I have my number line, I know that my mean is 3, and I have this point, -2. What's the distance between those if I measured it with a ruler? It's going to be 5 units. So that's what that represents. So 5, that's the first one. 4 minus 3 is 1. 0 minus 3 is -3, but we're taking the absolute value, so it's 3. 6 minus 3 is 3. 11 minus 3 is 8. Minus 5 minus 3 is -8, but the absolute value makes that 8. 7 minus 3 is 4. 3 minus 3 is 0. 9 minus 3 is 6. And -3 minus 3, again, is 6. And we're going to divide by the number of data points. Let me check that I didn't miss any. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's good. We're going to divide by 10. Again, all of these guys, these are all the distances between each point and the mean. We're looking for the average distance. So we add this together, and we get 5 plus 1 is 6, 9, 12, 20, 28, 32, 32, 38, 44. So this is 44 over 10, which is, of course, 4.4. So the mean absolute deviation of this data set is 4.4, which means on average each data point is 4.4 units away from the mean.